Hi kids, this video is the last one before winter break and it is a good one. I can't believe I get to end the our pre-winter break on such an awesome concept, the accumulation function. Please highlight this in your notes. The accumulation function as a convention, and especially as we're just starting to talk about the accumulation function, is usually referred to with a capital F. And you could even read in a book or hear me say cap F when we're talking about an accumulation function. And I do want you to kind of think about like snowfall. Snowfall, as snowfall continues, the snow accumulates. We're just not going to be accumulating snow. We're going to be accumulating integral values. Capital F with domain values x is an integral. But it's an integral where you start at a number a, but you don't stop at b. You stop at 1. Then you stop at 2. Then you stop at 5. Then you stop at -2. Your domain values are upper limits of integration. Your range values, your domain is what goes in, what comes out. Your range values are integral values. Right? You've been doing this for a long time. Functions, input, domain, in, do something, and get out values. Domain, in, range, out. What's going in this time is an upper limit of integration, your stop place. What comes out is what was the integral value when you stopped at 2. What was the integral value when you stopped at 5? That is the accumulation function. So it gives the accumulation. Notice that I put quotes around area because sometimes integral values are negative. Sometimes integral values are positive. Sometimes integral values are 0. So that's why I have the quotes around area, because it's not true area necessarily. Between the horizontal axis, right, usually the x-axis, and the graph of your integrand from A, which is your start, to different places to stop. That's kind of weird. Little f is the integrand. And if you'll notice, little f has t's in it. Sadly, I always feel bad saying that, saying this. The t is called the dummy variable. It's called the dummy variable because you've been dealing with functions for a long time. When I give you a number for x, you go across the equal sign and you look for x. For example, when you were in Algebra 1 and I gave you, f of x is equal to 2x plus 1, and then I said, what is f of 2? You went and found the x and you replaced the x with 2, right? You took the 2 and you put it in place of x. Well, now if I tell you what is capital F of 2, you go across the equal sign and you look for an x and you put an 2 in for x. But that's why you can't have an x here or here, because you're like, am I supposed to put the 2 there as well? No, you're not. Little f is the integrand. It is a graph that you are doing the integral under. Right? So capital F gives the accumulation values between the axis and the graph of little f from A to x, and x is going to change. A will not. The starting place is a number. A is referred to as the starting value of the accumulation. That will not change, but x will. So let's do an example. Example 1. And we're going to do this example the long way. It's going to take us a while to get through this example, and then I'm going to show you a shorter way. But I want to develop the concept. So given the following graph of A of t, which is 9.8, technically t to the 0, right? Here's a graph of 9.8. Please draw this graph in your notes. And please make note of the units. I want to actually calculate the following accumulation or integral values. Of the accumulation function. I probably shouldn't put the integral values there because the accumulation function means that you are going to input x's here, and the stopping place is going to be under the graph of A of t, where A of t is your height and dt is your width, and the range values are integral values. So we are just going to plug and chug, right? I'm just going to keep changing x. So right now, x just has a space, right? I mean, x is holding the place for 1. So when you put 1 into here, notice over here on my graph, I drew this height. I have a height of 1, but what is my width? I couldn't really draw that. I just, right, because I can't physically draw this width. This width is what? 1 to 1 is a width of 0, so what's f of 1? 0. But what happens when you change that 1 to a 2? Starting at 1, going to 2, under the function 9.8. Starting at 1, stopping at 2. What's that integral? I don't need, this is geometry, right? I can do this with just straight up geometry. That is a rectangle with a height of 9.8 and a width of 1. How about when I change the x from a 2 to a 3? Do you see my accumulation happening? I did stop at 2. Now I went back to start at 1, but stop at 3. I accumulated more, right? Integral values. My height of that rectangle is still 9.8, but what's my width? Can you see what's happening here? Accumulate more. Go to 4. Height is still 9.8, but width is, lastly, change x to 5. Accumulate. You have a rectangle now under the function A of t with a height of 9.8 and a width of 4. Can't I keep going? Can you see that I could do capital F of 6, capital F of 60, capital F of 700? Can you get me a rule for any x? Can you get me a rule for any x? I think you can. And if you can't yet, let's plot some points. F of 1 is 0. Capital F of 1 is 0. Capital F of 2 is 9.8. Capital F of 3 is not 9.8. It's one 9.8 and another 9.8. Hey. Capital F of 4 is 3 9.8s, right? Capital F of 5 is 4 9.8s. You're not surprised that that is a linear function, right? With a slope of 9.8. What? The rule without integrating, the rule is 9.8 times x? No, not x, right? 9.8 x what? Minus 1. I need you to understand what you've just freaking done. You had an accumulation function. And we accumulated by changing x. right? Are changing our delta t. But we looked at our pattern and we found a rule that gives the same answers without integrating. We went from an integral equation to an algebra one. But I get the same values. I don't have to integrate. I don't have to integrate to get 9.8 times 1, 9.8 times 2, 9.8 times 3, 9.8 times 4, or 9.8 times anything. That's powerful. That's powerful. As a matter of fact, what's my domain? I've used integer values 1, 2, 3, 4, 5, but if I get a rule for any x, can't I plug in anything like 0? Let's do the algebra first. What would 9.8 times 0 minus 1 be? Right? Truth? What happens if you did it up here? If they're the same, they have to give you the same values. What is cap f of 0 when you had the integral equation? The function height was still 9.8, but what was your dt? Going from starting at 1, going back to 0, is this rectangle. It is this rectangle, but the integral value is negative because your dt was negative. Yes, I got the same thing. But when I plot the point, what happens when I plot the point? When x is 0, what is the integral value? Negative 9.8. And then can't you see that I could keep going? Negative, right? Because after all, I could expand the interval I'm looking at. There's the graph of a of t. I could keep going, -1, -2, -3. I could keep going forever and ever in either direction. And I could use either the accumulation expression or the algebra expression. That's freaking nuts. Now, I want you to think about the units that we're dealing with. A of t units are what? I told you to make note of the units. Meters per second squared. What are the units on your width? The integral values. Integrating under acceleration gave me what? What? Capital F is velocity? What is happening right now? What is happening in my life? Capital F is velocity? Capital F is velocity? What? It's wait a second. Whose acceleration then? Let me let that sink in for a minute. This is craziness. This was t to the 0, right? 9.8 t to the 0. When we plugged and chugged and came up with an algebra rule, what did we come up with? An x to the first, right? You're used to going the other way. I gave you a velocity. What if I said, hello, velocity is 9.8 t minus 9.8. There's my velocity equation. What's acceleration? How do you find the acceleration? What's the relationship between velocity and acceleration? Acceleration is the derivative of velocity. A of t. A of t was 9.8. Thank you very much. 9.8 was A of t. I knew that when I integrated under A of t, I got velocity back. That is crazy. Accumulating area under acceleration yielded velocity. Those of you in AP Physics are going, duh, Mr. Getz taught us that already. Yeah, but he didn't teach you why, now did he? This is why. And here's what's awesome. You all know an awful lot of stuff about the graphs of derivatives. And if I give you the graph of the derivative, you can tell me stuff about the original. Notice I gave you acceleration. Acceleration is the derivative not only of velocity, but it is the derivative of capital F. If it is the derivative of capital F, then you can tell me stuff. What do you know about capital F? Well, you know its derivative is always positive. Since capital F's derivative is always positive, capital F must always increase. Right? Isn't that nuts? Capital F is 9.8 times x minus 1. The derivative of capital F, take the derivative of cap F, take the derivative of a linear function, you get the constant 9.8. The derivative of capital F was the very graph you were drawing your rectangles under. They were the same. That is nuts. Nuts. Since the derivative, the blue graph, is always positive, capital F must always be increasing. Hello, it is. My derivative is positive because I'm always increasing. You know what else you know? Since the derivative has no extrema, capital F has no change in concavity, which means it has no concavity. Hello? Whoa, you know an awful lot about what the first derivative tests tell you. And you can find, with using the first derivative, you can tell me about increasing, decreasing. You can tell me about max and mins. And even from the graph of the first derivative, you can tell me concave up and concave down. And boy, we learned this last 2 units. The accumulation function is an integral. F of t with your dummy variables, t is the integrand. How are capital F and little f related? They are inverses of each other. Little f is the derivative of capital F. Little f is big F's derivative. Little f is called the derivative. Its inverse is called the antiderivative. Woot woot! Celebrate! Whoa, this is a big freaking deal. This is huge. It's so huge. It is called the fundamental theorem of calculus. This is what Isaac was figuring out when he was isolated during the pandemic of his lifetime. He figured out the fundamental theorem of calculus. What have we done? I don't know. I've watched The Mandalorian. That's what I've done. The fundamental theorem of calculus. What's the root word in fundamental? Hello, fun. If you write no other theorem down, you should write this theorem down. If little f is continuous, all I need for the fundamental theorem of calculus is continuity. That's why continuity has been stressed to you over and over and over again. If you have continuity on a closed interval, which means all of our lovely functions from our past, all our polynomials, sine and cosine, they are, no matter what interval you choose, continuity. Rational functions have just singular places that they may be discontinuous, and everywhere else they are continuous. Notice I don't need smooth. I just need continuous. If little f is a continuous function, a continuous graph on some closed interval, then little f has an accumulation function associated with it, right? Little f just has to be continuous, graph of little f. Then there is an accumulation function that is associated with it. And further, my accumulation function, f, the big F, has a derivative at every point. and its derivative is little f. Whoa. Whoa. Right, now write that down. I'm going to pause for a minute. You write that down, please. And while you're writing that down, I want to remind you of Algebra 1. I can add 5 to both sides. I can divide both sides by 2. I can square both sides. I can also take the derivative of the left side of this equation. If I take the derivative of the left side of the equation, that's what I have. But that's not legal. You cannot take the derivative of the left side without doing what to the other side? Notice I am taking the derivative with respect to x. That's what this statement is. But notice what I get out of that. I want to remind you that if you take x and you cube it, but then you cube root it, what do you get back? Just x. I took little f and then I anti-differentiated it. But then I differentiated it. And you know what derivatives and anti-derivatives do to one another? They undo one another. And just like x came dropping out of this, f of t comes dropping out of the derivative and the antiderivative notation, and I don't need the dummy anymore. X gets taken along for the ride. Crazy. That is absolute fundamental craziness. When you have a derivative and an antiderivative, they undo one another. And I can, not only do they undo one another, I can get rid of my dummies. My dummy variables are not required anymore. Everything in a green box is, in those green boxes, is either integral notation or derivative notation. And when you derivatize and antiderivatize at once, it's as if you did nothing. Just like when you cube and cube root, you really didn't do anything. The original comes back out. This is so important. If we were in school, I would tell you that when the bell rings, make sure you go out of my classroom, turn right, and look up. This is painted on the wall above the lockers. These are our lockers right outside, room 324, and that's painted on the wall. Look for it next time we're back in school. I told you it was going to take a long time before we got to example 2, but now example 2 is going to go a lot faster. So notice that I have the graph of little f, the graph of little f. Given that the accumulation function on little f, capital F accumulates under little f. And I'm going to tell you, answer the following questions, but I'm going to give you the closed interval from -3 to 3. Answer the following questions. Wasn't expecting that, were you? You were expecting me to plug and chug, weren't you? Like we did in example 1. No, not gonna. I am going to ask you, what are the increasing and decreasing intervals on capital F, not little f, not little f. Hello, little f is the derivative of capital F. I do not see any values of capital F. I do not see the graph of capital F, but I see the graph of its derivative. And what are the increasing and decreasing intervals on capital F? Those intervals are the intervals where its derivative is positive and negative. right? When someone's derivative is positive, your graph is increasing. When the derivative is negative, the graph it came from is decreasing. Look at the graph of the derivative from -3 to 3. What is the graph of the derivative doing? Positive and negative. Always positive. Therefore, since, and you don't have to write this. This is in your thought bubble. That's what you're thinking. Now write, because it said justify. Since the derivative of capital F is the graph I'm looking at, and the graph I'm looking at is positive on -3 to 3, capital F is increasing on -3 to 3. Whoa. Whoa! I didn't do any integrating. I didn't plug and chug, but I already know on the interval from -3 to 3, the graph I can't see is increasing. What are the concave up and concave down intervals? And I know you're thinking I need the second derivative. No, you don't. I taught you how to read concavity from the derivative. From the derivative, what is the derivative doing? The derivative is increasing or decreasing. That's what you think. Then write. Since the derivative of the graph I don't see is the graph I see, on those intervals, right? I could write that a little bit better, but I'm saving time, right? Hello, I'm the graph of the derivative, right? I can't make that big, right? I keep changing colors and just that you are looking at the graph of the derivative. Look at this nonsense. What is the instantaneous rate of change? What does that mean? Instantaneous rate of change. What D word does that go with? Derivative. What is the derivative of capital F? This is what they're asking you. What is the derivative of capital F at 2? I don't see the graph of capital F, but the derivative of capital F is little f. And what is little f at 2? Oh, snap. Wasn't that nice? Crazy. Now, all of these questions were answered by looking at the behavior of the derivative graph. The behavior of the derivative graph and of that y value on the derivative graph was a derivative value on capital F. So some of you might be saying, whoa, Ms. Getzo, you haven't been paying any attention to the accumulation value. That's because I didn't accumulate anything yet. I was looking at the graph of the derivative and answering, and I was looking at the behavior of the derivative to answer behavior values on the original. I did not get any accumulation values. Please get your calculator. And now I'm going to ask you for some accumulation values. Now I care about the 0. Now I care because I'm actually using the function rule. Now, example 1 was a constant function. I could actually go from integral to algebra. I can't go from integral to algebra here because my capital F, right? I can't use geometry to find the exact area from -3 to 3. Capital F is start at 0. Notice I can't use X, right? I've already used X. So I have to change the X. I have to use the dummy. And I actually now have to plug and chug. So what is F of 0? I don't need a calculator for this. Whoops, I wrote X there and I meant T. Right? If your bounds go from 0 to 0, what's your integral value? Yep. But because this isn't a geometry shape, when you need to compute f of 3 at this point in your math career, you need to math 9 this. So please do put 1/4 x squared into y1, put this into y1, and then hit math 9. So math 9 of y1, starting at 0. It is super important that you start at 0. And notice the start value does not change. You're going to get 2.25 or 9/4 out of that. So look at what this looks like up on the graph. Capital F of 0 is 0. Integrating, not behavior. I'm actually integrating. That integral value is not a geometric shape, right, that I have a formula of. The width is positive and all the heights were positive, so you should not have been surprised to get a positive 9/4 out of that. But now what happens when you do f of -3? Just hit second enter on your calculator and change the 3 to a -3. What do you get? Are you surprised? I hope not. You can see visually that those two blue pieces are the same because of the symmetry of that parabola. However, because you are starting at 0, that does not change. Your width is negative and all your function heights are positive. So to the right of 0, you had positive times positives, which was sum them up, positive. But to the left of 0, because you were starting at 0, your width was negative and all your heights were positive, which is why you got a -9/4. Now, let's put all of that together. Put all of the information together. F of 0 is 0. F of 3 was 2 1/4. F of -3 was -2 1/4. And what about the other stuff we figured out? F is increasing the whole time on -3 to 3. We also know F is concave down from -3 to 0. And we know that capital F is concave up from 0 to 3. Without doing a whole, just looking at the graph of the derivative, I got all of this from the first derivative test. And then I got a couple of values here from actually integrating. But again, we used Math 9, right? We had our calculator, and you will to do anything like that. But notice what I can draw. I can now draw increasing concave up, increasing concave down. And doesn't that kind of look cubic? What's the derivative of a cube? A square, right? OMG, we're going backwards. Instead of taking derivatives and power downing, we are taking antiderivatives and power whatting? OMG. OMG! Math is cool. All right, kids. This, again, was a great lesson to end on. There is a handout that goes with this lesson. It is very short. Please do it. Try to do it as soon as, when you finish watching, please try to do the handout. It is a short handout. I've written all over it. You'll see my thought bubbles, right? I'll have this on there. I'll have all kinds of arrows and comments all over it. This is a super important concept. So I really want to make sure that you nail it. And I believe that you can. And I am sure that over the break, you will be celebrating and relaxing and thinking about the first fundamental theorem of calculus. All right. I will see you in our next live session. Take care.